Good evening and welcome to the session number 9 from the chapter of gravitation. The topic is the Kepler's second law of planetary motion, and today we will be finding the areal velocity of the planet. So before proceeding with this topic, we will first of all revise the Kepler's second law of planetary motion, and we have already studied about the Kepler's laws in the session number 7. So as per the Kepler's second law of this planetary motion, the planet sweeps out equal areas in equal interval of time, or in other words, the area swept by the lines joining the sun to the planet sweeps out equal areas in equal interval of time. So, and this is called the areal velocity, and the areal velocity is given by this equation, that is d upon dt is equal to L upon 2m. Okay, so this is the formula which we will be deriving just now. So here L is what? It is the angular momentum of this planet. Now, if the planet is sweeping out equal areas in equal interval of time, then it means that the planet will move faster when it is near to the sun, and it will be moving slower when it is far away from the sun. So in this way, we can say that this Kepler's second law of planetary motion is a consequence of the law of conservation of angular momentum. Now, the planets they revolve around the sun in elliptical orbit, but since the orbit is slightly eccentric, therefore we can consider the orbit of this planet to be circular in shape, and this is basically for making the calculations simpler. Now, if the orbit in which the planet is revolving is taken to be circular in shape, then in that case the area swept by the planet, let us say from this point A to point B in time delta t, let us say the area swept by the planet in moving from the point A to the point B in this orbit in time delta t, this will be equal to half into. Now, if this orbit is very large, and if this is a circular orbit, so in this case what I can do is I can simply use the formula of the area of triangle. Now I could simply draw this this portion with the help of another diagram here. Now let us say like this. This is the point A, this is the point B, and this is the point where these two lines are meeting at the sun. Now, since the orbit is very large, so though this is an arc, AB is an arc, but it can be taken as a straight line. And this is primarily, we are doing this in order to make this calculation simpler. Now, if this is a straight line, then the value of AB will be equal to V into delta t, where V is what? It is the orbital speed of the planet. So AB will be equal to V into delta t, and let us now the area of the triangle is equal to half into base into the perpendicular height. Now this perpendicular height can be taken equal to the orbital radius, say r. So the area of the triangle can be taken as 1 by 2 into r into V into delta t. So here I will be writing this value, that is A is equal to 1 by 2 into R into V into delta t. And so for the small time interval, we can write this equation as dA A is equal to 1 by 2 R V dt. Now dA upon dt from here will be equal to 1 by 2 into V into R. This can further be written as, I will just multiply this equation in the numerator and denominator by m, where m is the mass of the planet. So this is equal to mvr divided by 2m. And mvr is the angular momentum, so L upon 2m. So the areal velocity of the planet is equal to L upon 2m, and this is a constant. So if this is a constant, we can say that the area swept by the planet sweeps out equal areas in equal interval of time. So this is an important formula, that is dA upon dt is equal to L upon 2m. So we will be solving few numerical problems based on this formula in the forthcoming sessions. So till then, have a nice day. Bye.